All right, so the outline, like I said, we're going to have a look at how to calculate work. Basically, we're going to look at the definition, work and kinetic energy, different ways you can look at how work is applied, one-dimensional, two-dimensional, three-dimensional, where vectors come in play again, and then how we can calculate the power and the work and energy example at the end, just to see that you do understand all the equations that I'm throwing at you. Then next is energy, different kinds of energy you get, potential energy, kinetic energy, and then we're going to have a look at the conservation laws, conservation of energy, what that entails, and then finally some energy methods, the principles, and how we can use energy balance equations to solve problems, state 1 and state 2 and the differences there. And then we're going to end it all off with another example just to see if you understand all those equations. All right, so if we consider a particle in the three-dimensional space, we can calculate the work as being the integral for this particle moving from point A to point B, where F is the force vector and R is the position vector for cases A and cases B. You can see they're typed in bold, meaning they are a vector, so they've got different components. It's got magnitude and a direction. All right, so the process involves the dot product of the two vectors, and then you can calculate that. So if we consider one-dimensional first, there is only the x direction in this case. There's a particle moving from point A to point B, and we now need to calculate what work was required to move it from point A to point B. And then that integral can be reduced to the work between point A and B as being the integral of the force as a function of x, because it's only one direction. So only the x direction. And the units is Newton meters, so it's the force times the distance. That's why newtons is the force, distance is meters, so your unit will be Newton meters. That is the units of work, and Newton meters, of course, is also joule. So Newton meters is the same as joule. All right, so now we have a look at Newton's laws that we've used last week. So taking Newton's second law and the definition of acceleration. Definition of acceleration is basically that acceleration is the derivative of velocity, and velocity is the derivative of displacement. So F equals ma is Newton's second law. We then can rewrite acceleration as the derivative of velocity, and we also know that velocity is derivative of displacement. That is the second equation. You can see it's just rewritten a little bit. And now we can go and we can merge these two equations together. You can see there's a bunch of writing there, but essentially it boils down to half m velocity squared of b minus half mass of a times this velocity of a squared. So that is how you calculate work for a one-dimensional case, where it's only moving in the x direction. Right, so kinetic energy is obviously, kinetic means movement. So if you move from point A to point B, your total kinetic energy will be the kinetic energy you have at B minus the kinetic energy you had at A. So that is the net kinetic energy. In mathematical terms, you can just rewrite it. Capital letter U usually indicates energy, and the subscript shows you which kind of energy it's talking about. So you can see the subscript K stands for kinetic, and then A or B showing you it's the kinetic energy at point A or the kinetic energy at point B. And that equals delta U subscript K, which is the net or the difference in kinetic energy for that state. Applying the original definition of work and the constant force, so there's a constant force applied, so the force is not changing. We can thus say that force times the distance that you moved in the one-dimensional case equals the work done. So if you know the force constant, 100 newtons, you know you are moving 2 meters, then it's literally 100 times 2. That equals 200 newton meters. So it's just multiply the force times the distance you moved, and you get the work done. So work done is force times distance moved, F delta x. That is for one-dimensional case. When we look at gravity, that is for vertical movement. So the force has to overcome the gravitational force. Gravity always downwards, and we are assuming downwards always negative. So that is negative mg. And the object moves a distance from A to B, which in this case is h, which is the height. It stands for height, h. So thus your work is mass times gravitational acceleration times the height it moved up or down, and that is the work done by gravity. It's again force times distance. In this case, the force is just mass times gravitational acceleration, where we usually just have F equals ma. Now it's F equals mg for when you're considering gravity. And then the distance is the height change for the particle. So if the mass is then released, if I release it, then it will accelerate downwards, and then you can calculate the work that gravity is doing on this particle as the negative mgh. Right, because the work is going downwards, direction is downwards, that's why it's negative. Lifting the object, the force is upwards, that's positive, so your work will be a positive value. And work can be positive and negative, and if we make sure that work cannot be changed, so literally the upwards equals the downwards, you can see that it equals 0. So essentially anything so my bottle that's standing here, if I move it, if it's sitting right there, again, gravity is pushing it down, or is pulling it down, but it's pushing back, or the bottle is pushing back, doesn't want to move, the tabletop's keeping it in place, so that's why the net force is 0. In the same case here, if I've got something and I hold it, you would have the force for me keeping it in the air, plus the force of the gravity pulling it down equals 0. So net force is 0 in this case. All right, so if we look at, for instance, one of our little boxes that we had last week, you know the free body diagram. This box is moving from A to B, and you have its gravitational forces pulling it down, normal force pushing back up. F is the force that's moving it to the right, and then you have some frictional forces that is pushing back against movement. And it's shown in the free body diagram as such. So then if we look at frictional forces, we can then say that frictional forces equals the frictional coefficient times the normal force, and in this case normal force equals mass times gravitational acceleration, so that F equals mu times mass times g. And again, if it's a constant force that is pushing this block along, we can then just again say that the force, frictional force times the distance it's being pushed equals the work done to overcome frictional forces. Right, then we get cases where the force is not constant, so the force is changing over the distance that this particle is moving. In this case, you can see the graph is an F, the force is on the y-axis and the distance is on the x-axis. So as the distance increases, the force increases as well, so it's not constant, it's changing. So then you need to take the average of the force over the distance traveled, which is half F in this case. So at 0, the force is nothing, and at x, the force is F, so then half of the total force of the maximum force. And the work done is again force times distance, so you can see half a force times x, which is your total distance traveled. So that is the case for when the force is not constant. And then we also look at a spring. So a spring does not like to be expanded or compressed, so whichever direction, if you're compressing it or expanding it, there will always be an opposite force to the movement. And in this case, it can be calculated as F being the force exerted by the spring equals the spring constant K times the distance you are compressing it or the distance that you're expanding it. And then the work that's required to either compress or expand the spring equals half kx, which is the force, times x again, because that is the distance that you're compressing it or expanding it. So if you're looking at a spring, it is half kx squared. That is how you calculate the force required to expand a spring or compress it. Half a kx is the force, because the force is not constant. As you go and expand or compress a spring, it changes versus the distance you are expanding or compressing it. So that is half, so half a kx, but then you need to multiply it again by x because that is the distance. Half a kx is only the force, but you want to know the work, so that's why you're multiplying it with x again to get the work required to expand or compress it. But then obviously we're not always going to look at one-dimensional problems. You can have three-dimensional problems where there's a little route you follow from A to B. It's not a straight line. And then you start working in vectors again. And this is the equation that we had at the beginning, where the force is a vector, but the r is a vector as well. So the position vector at A and the position vector at B is different, and it characterizes your movement in the three-dimensional space. We can boil that a bit down to two-dimensional. So this is again with reference to last week's free body diagrams. There's a force that is not, it's got a y component and an x component, so it's two-dimensional, and it's pulling along a crate. So now you have a two-dimensional case for calculating the work. So you'll have a work component that goes to the right positive x-axis, and you've got a work component that goes upward. And yeah, so you can break that down. So the force vector you can break down to its three components, the x, y, and z components, as well as your positional vector r into its x, y, and z components. And then you can, again, use the same method that we did with Newton's law in calculating each component separately. It makes it a bit easier. And then obviously the work, the derivative of the work, you can now go in each component you can derive. So that is the x component of the force times the derivative of x, dx, dy, dz. So you can break that up. It'll make your life easier if you do calculations for them. And then total work is the integral of each of those components. And then you can simplify that equation as being half m v squared for each of those components as well. So you have the x component at point A and the x component at point B, so you need to subtract them from each other. Then you get the net movement or the net velocity, and that is true for each component. And then we can further simplify this equation back into its vector form, which is half m magnitude of the velocity vector B minus the magnitude of the velocity vector A squared. So we've gone and calculated the work and power required. That is the force over a distance. And now we can calculate how much it takes. That equals the power. So the work, it takes me a certain amount of work to move a component from point A to B, but it can take me an hour to do it. It can take me a few seconds to do it, and that is your power. So if your power is very low, it's very small power required to do work over a long time versus the power required to do it in a second or milliseconds even. So that's where the work that you've calculated, you divide the time into that, and then you get the power. So we've got forces, we've got work, which is in Newton meters or joules, and then we get power, which is joules per second, or also in watt. You can see if we say power is work done is force times distance, and you know distance over time is velocity, meters per second. So power is also force times velocity. Where we had work was force times distance. We now have power, which is force times velocity. And its unit is in watts, which is joules per second or Newton meters per second. So we have this example. There is a little ring on a round bar, mass m, slides on this round bar under a force of gravity along a rail from position r1, which is our position vector 1, to position vector 2 as shown in the diagram. Now you can see there's a little coordinate system there at the top showing you y is upwards, x is to the right, and k is out of the page. We now want you to calculate the work done by gravity on the mass, and it's given the mass has got half a kilogram of mass, and we give you the two position vectors. And the question is, determine the work done by gravity on the mass. Work from point 1 to point 2 is the force times the delta change in displacement. So we know it's moving downwards. We get our vectors, displacement or position vectors R1 and R2. So we want the delta, and delta R, in this case, is the vector 2 minus the vector 1. That is 5i plus 2j minus 2i minus 5j. All right, and that equals 3i minus 3j. That is our change in position. So because we are only interested in gravity, our force becomes the mass times the gravitational acceleration times the distance of our y component. Gravity is only exerting a force downwards into the vertical direction, so we can basically ignore the x component of our position. So then that becomes the mass is 0.5 times 9.81 times the y component, which is that one there, -3. And that will give you an answer. I don't have a calculator with me now, but it's approximately 14, -14. All right, so the fact that it's a negative, meaning it's downwards, yeah? Why? The negative, because it's gravity, it's going downward, the force, and our convention is x and y as being upward. So if you would have taken that mass and moved it back up to its initial position, the force would be positive because the force is going upward. But because it's gravity, acceleration is downwards, it is negative. All right, now we're moving on to energy. Energy is the capacity to do work. So I've got the capacity to move or do work depending on my placement or where I'm at. We get different ones: gravitational potential energy, elastic potential energy, which is a spring or rubber band, and kinetic energy is something that's already moving. So we know that work done by gravity can be calculated as mgh. However, the work done has gone to increase the store of gravitational potential energy within the body. So if I move it higher, its gravitational potential energy will increase. If I move it lower, it will decrease depending on its height from the datum point. So that's what it's mean. You can change that either if you put something higher or lower, its gravitational potential energy will change as a result. And also if you move it, or in the case where you have two situations from it's moving from point A to B and its height changes, that can either increase or decrease its potential energy, gravity potential energy. And then similar for elastic potential energy, like I said, that's for a spring or for elastic band. Again, to calculate the work is half kx squared, and then that is also an indication of its potential. So if we increase the store of potential elastic energy with the spring, then that is the equation, UPS potential elastic energy. Elastic potential energy is then that equation as well. And then lastly, kinetic energy is when something is moving and the work done to move a body has gone in to increase the store of its kinetic energy. So if it's moving at 1 meters per second and it's changed over to moving at 2 meters per second, its kinetic energy potential has changed, it's increased. All right, and then mechanical energy is basically just the summation of all those three. So the total mechanical energy of a system or of a particle is its gravimetric potential energy plus its elastic potential energy plus its kinetic energy. So those three equals mechanical energy. And now then we can use all that, knowing that its potential at point A and we know its potential at point B, we can now introduce conservation of energy, where we say that energy is not lost or created, it merely changes. So now we can say, right, if something has got this state at point 1, got this many potential energy, this much kinetic energy, and then it changes into state 2, and its potential and kinetic energy has changed. The first instance, total mechanical energy is the same as its mechanical energy at point 2. So that's what's mean. It's essentially the conservation of mass as well. No mass can be created or deleted. That's the same with energy. The energy is the same at point A, at point B, at point C. It stays the same. So that is very useful when you need to do some calculations of its states at point 1 and point A. So, for example, a falling body loses potential energy as it loses height. So that is when you look at the equation mgh. So its h value is decreasing, meaning its potential energy is decreasing as it reduces its height, as it's falling. But it gains an equal amount of kinetic energy because it's gaining speed. Because of the gravimetric acceleration constant, it is constantly accelerating as it falls through the air, so its kinetic energy is increasing while its potential energy is decreasing. So that's where total energy is the same, it's just changing over from potential energy to kinetic energy. That's essentially what conservation of energy is all about. So we get a nice little diagram showing you that you get your potential energy and your kinetic energy of a system, and then we also introduce any work done on the system, as well as any work lost, so work that the system does. So W subscript G is the energy gained by the system as a result of work being done on the system. So that would be external forces either prompting it into movement. And then the energy lost from the system as a result of work being done by the system on the surround. So that can be frictional forces that it needs to overcome in order to move. And then the other two is the kinetic and potential energy that we just talked about. So those are the four main forces that's in play if we look at conservation of energy. And this is the very nice equation that sums it all up. So you can see there's an equal sign, which means that situation 1 or initial situation equals the final situation. So the energy at the start equals the energy at the end. In this case, we've got mechanical energy at 1, which is the kinetic and potential at point 1, plus the work gained, so that is external forces that's being exerted on the system, minus the work lost, because there's work that the system needs to do to get it from point A to point B, and that equals then the mechanical energy at point B, at point 2. So energy at initial point equals energy at final point, and that energy can be broken down into its mechanical energy as well as the work gained and lost. All right, so we have this system of mass 1 and mass 2 that's connected by a rope over a pulley. And they give the mass 1 is 200 kilograms, is connected on a rope over a pulley to a mass of 400 kilograms, which is mass 2, and is shown in the figure. Initially, M1 is held in position, so there's no movement, and then it is released and allowed to slide over the horizontal surface, and that surface has got a coefficient of friction of 0.2. Now, you need to go and calculate what is the velocity of the masses when they have moved 2 meters from their starting point, which was in a resting position. And there's a bunch of assumptions that you need to make. One of them is there's no air resistance, so you don't need to worry about that. Other one is the rope is not stretching, it's a rigid rope, so there's no elastic forces in there. All right, so when we use the conservation of energy equation, which is the mechanical energy at point 1, plus the work gained minus the work lost equals the mechanical energy at point 2. We can see that mass 1 is moving, but it does not change in height, meaning that its potential energy is not changing. It's got constant potential energy. So the change in potential energy for mass 1 is 0. There's no change. It's the same potential energy. Its kinetic energy changes because it's increasing in speed, thus its kinetic energy is increasing. So there's a positive addition of kinetic energy. If we look at mass 2, it is changing in height, so it's dropping by 2 meters. So it's losing potential energy because it's going close to the ground, but in the same time it's also gaining kinetic energy because it's speeding up. And then because of the frictional forces being exerted on mass 1, there is work being lost from the system because it needs to overcome the frictional forces. All right, so then when you use this equation here, you can now rearrange a bit because there's a bunch of stuff that you don't know. So there's no work gained, so that variable you can disregard. If we then go and we say the change in potential energy from UP1, so we can just say UP1 minus UP2, that is negative delta UP12, because the system is losing effective potential energy because the only potential energy change is in mass 2, and it's dropping in height, so there's potential energy decrease in the system. So that's why you got change in potential energy as being negative, because it's losing potential energy in a sense. All right, then the same goes for that we can just keep. That is the frictional forces, and we can just say that is K2 minus UK1. All right, so we've gone and simplified it a bit. Now, if we look at this term here, that is essentially just the change of potential energy of mass 2. So that is mass 2 times the gravimetric acceleration times delta H, which in this case is 2, minus the frictional forces, which is of mass 1. It's the frictional constant coefficient 0.2 times the normal force of mass 1. Normal force is also mass times gravimetric acceleration, and that equals then half K2 is a half mass 2 v2 plus a half mass 1 v2 for state 1 minus a half mass 2 v2 plus a half mass 1 v2 for state 2. You understand that the whole, I'm dividing it up in two states, but I'm considering both masses acceleration, also velocity. That's why I'm adding them together. So because they're both moving from rest, you could say the initial, which is K1, there is no V's there, so this whole term here can be disregarded because they're standing still. And then this whole equation can be rewritten as mass 2 G delta H minus M1G, it's mass 1, yeah, equals half mass 2 or mass 1 plus mass 2 V squared. Because we don't really know what the height is at the start of state 1, we don't know where mass 1's height is in state 1 and mass 2's height in state 1, but we know the difference is 2 meters, the movement of mass 2, mass 1 having no increase or decrease in height, so that component's potential energy stays the same. The potential energy of mass 2 is decreasing, so then we can say the difference between the potential energy of the two states is then mass 2, because that's the only one that is changing, times the gravimetric acceleration times the distance changed, which is 2 meters. And then we got our work lost, which is our frictional forces, and then equals the kinetic potential energy. And now you can just go and put all the values in. The only unknown in this case is our velocity there. Oh yeah, you're right. Yeah, so that distance is delta x. Delta x, thanks for that, yeah. Yeah, so that part only there I showed initially is just the force. Obviously you need to multiply that by the displacement, which is 2. So that's where the delta x is there, 2 meters it moved. All right, so then the only unknown is the velocity. You can then calculate velocity and get the answer.